All right, so welcome to Hoon Academy Lesson 2. Using the subject, learning more about Hoon syntax and learning a bit more about Aura's Hoon's type system. Okay, so recall that in last lesson, we learned that any knock code, which is the machine language that underlies Urbit, has two parts. And those two parts are going to be the subject, which corresponds to the data input, and the formula, which corresponds to the computation that you're doing on the data input. And recall that because Hoon has a very tight correspondence to knock, any Hoon code also has the same structure of subject and formula. So we learned the rune Tisgar last time, right? So it takes two children. First child is going to be something to set as a subject. Second child is going to be something to set as a formula, something to do with this as a subject, right? So to see an example of that, here, we're going to use a Tisgar rune. We're just going to set the number 1 as the entire subject, and then we're going to use this dot to just return the whole subject. So then we get back the number 1. Here's a slightly more sophisticated example. So here we're going to use Tisgar to set the cell of 1 and 2 as a subject. And then we're going to use .tis. Remember, .tis takes two children and gives you a yes if they're equal and a no if they're not equal, right? And what are these minuses and pluses here? Does anybody know what these minus and plus are referring to? It's a kind of notation that we learned last lesson. What is this .tis minus plus doing? Yep, position in the tree. Yep, so this is the Lark notation that we learned. And this is telling us, remember this hep is going to get the left branch and the lus is going to get the right branch. So we're saying with this 1, 2 as a subject, we're going to compare equality of the head and the tail of the subject, which is just number 1 and number 2, okay? So press enter and we get a no, because 1 is not equal to 2, all right? But if we change this to 1, 1, and run the same code, then we get a yes, right? Because 1 is equal to 1. Okay, so we also learned that any Hoon code we type in the dojo is implicitly wrapped with a hidden Tisgar. There's a hidden Tisgar there, which composes it with the standard dojo subject, okay? So if I just press dot in the dojo, and I press enter, it's going to print out this huge thing, or this big thing, okay? What is that? This is a bit mysterious right now, but this is basically the pretty printed or summarized version of this gigantic dojo subject, okay? So we don't need to understand this right now, but we do need to know that's what this is. And that this demonstrates that this implicit wrapping is there, okay? So in last lesson, we learned about families of runes. So runes are organized into families depending on what their first character is. And we're going to learn more runes in the Tis family, starting with this equal sign, okay? So this family of runes is all about modifying the subject. So the first new rune that we're going to learn is Tislus, okay? So Tislus takes two children. It computes the first child and sets that as the head of the subject. So it doesn't replace the whole subject, but it sets this as the head of the subject and makes the old subject the tail of the subject. So the old subject is still there, but this is just, this new thing is attached to the head, okay? And then in the second child of this Tislus, we have some Hoon code to do against this new subject that we just changed, okay? So let me show you a graphic that'll make it clearer what this means. So we have some old subject, which is some binary tree, right? And then we're going to perform this Tislus X, and that's going to create this new tree structure that looks like this over here. Okay, and that's just this X is added to the head of the subject, and the old subject becomes the tail of the new subject. Okay, and that looks just like this. If you're doing it in cell notation, you're making X the head and old subject the tail. Okay, so that's what this rune does. Now let's see a simple example of using this rune. Okay, here, let's set the number 2 as a subject. Then we're going to use tis lust 1 to pin 1 to the head of the subject, and then dot to return the whole subject. And what's that going to give us? The cell of 1, 2, because it took this, put it as a head, took this, put it as a tail, and then we return the whole thing, right? Similarly, if we start with a subject of the cell 2, 3, and then we do this tis lust 1 to pin 1 to the head of the subject, and then press dot, we're going to get the triple 1, 2, 3, because it put this as the head and put this as the tail, okay? And to prove that it's the head, we can do the same code, but instead of returning dot, we can return hep to grab the head of the subject, and that's going to be 1. So 1 is what was pinned to the head by this tis lust, okay? All right, any questions on that? Okay, so moving on, let's introduce another new rune, tis faz. Tis faz does the exact same thing structurally as this tis lust does, okay? Same function, except it also attaches a face, or a face is what we call a name, to the new thing that you're pinning to the head, okay? So same thing, but you're also putting a name on it, okay? So here, let's set the number 2 as the subject. Then we're gonna say, let's pin the number 1 to the head of the subject with the face A. And then let's grab the entire subject with dot, okay? And then we'll see that the entire subject is a cell with A equals 1 as a head and 2 as a tail, right? Because we're just pinning this to the head. We can also do the same thing, but then grab A to see that indeed we gave this this 1 the name of A, and then we grabbed it, right? And we can do the same thing, set 2 as a subject, pin A equals 1 to the head of the subject, and then do a hep, and then that's going to give us A equals 1. Just for sanity check, guys, why is this hep getting this A equals 1? Can anyone tell me?
Lark notation.
Yep, Lark notation. This grabs the head of the subject, which is that. All right. So we can use this rune also with the dojo subject, so we don't have to manually set some subject. For example, we can just do, let C be the cell 5, 6, 7, and then just grab C. That gives us 5, 6, 7 back, right? Similarly, we can do let C be 5, 6, 7, and then we can do this hep, this LARP notation, to grab the head of the subject, and that's going to give us C equals 5, 6, 7, because with this operation, that's just what we put in the head of the subject, okay? We just put this there, and then we grabbed it with this hep. Okay, so any questions on that tis-faz rune? Otherwise, we'll be moving on. Okay, so the next rune is called tis dot. So the tis dot rune is going to take one location of something in the subject, change that to a new value, and then compute something against that new subject, okay? So let's see an example of this tis dot. So here, let's set the cell A equals 1, B equals 2 as a subject. And then let's use this tis dot to set A to be 100, okay? So tis dot, first argument says what you want to change. Second argument, 2. And the third argument is what do you want to do with that new subject. So the third argument to this is just going to be dot. We're just going to say what we want to do is just return the whole subject, okay? So we get a equals 100, b equals 2. Set this as a subject, change a value to something else, return the whole subject, okay? And we can do this with LARC notation as well. So start off the same way. Instead of a here, you can use this hep. And then this hep also refers to the head of the subject. So this also grabs this a. And then we can use dot. Same thing. We get a equals 100, b equals 2. And of course, we can do this in just in the dojo subject as well. Set C to 5, 6, 7. We use this tis dot to change C to 1, 2, 3. And then we return C. We get 1, 2, 3. Okay. So let's introduce another rune, very similar rune. Tis col does exactly what tis dot does, except you can give it multiple pairs of things at once, okay? So you don't need to just give it one address and one new value, but you can give it a bunch of different things to change, okay? So one important thing about this rune, this is the first rune that we've seen that doesn't take a fixed number of children. It can take an indefinite number of pairs of children, okay? So here we have child 1, child 2, child 3, child 4, and that can go on indefinitely. And then you need to close the rune with this tis to mark where you want it to stop parsing. Since this rune is undefined in how many children it takes, you need to tell the parser when you're done giving it inputs, okay? So let's see an example of this rune in action, okay? So we're going to set this cell of a equals apple, b equals banana, and c equals cherry as the subject. Then we are going to use this tiscol to, We're going to use our rune tiscol to say, let's change A to avocado, and let's change B to berry. This tis closes the children for this rune, and then we give it a dot to say, let's return the whole subject. And then we get back A equals avocado, B equals berry, like we changed it, and C equals cherry, okay? Any questions on that? All right, so to conclude the section, here are all the tis family runes that we've learned so far. So tisgar and tisgal, we learned last lesson. Let's set something as a subject and do some evaluation against it. And then these 4 new runes that we just learned to modify the subject and do something with that modified subject, okay? All right, any questions on any of these runes? All right, so in that case, we'll be moving on. We mentioned that the dojo subject, we keep bringing this up. It has a lot of useful definitions and standard utilities, okay? So let's actually start to use that. For example, something that it contains are lots of predefined functions, or what we call gates, which allow us to do things like basic arithmetic, okay? So let's learn a new rune called senhep, okay? Senhep takes 2 arguments, a gate that you're referencing that you want to call, and the argument to the gate. Let's see a simple example. Senhep add the cell of 1 and 2. That's going to give us 3. What happened is somewhere in the huge dojo subject that's implicit here, there's something defined called add. When we gave this first argument to this senhep, it looked for something called add and it pulled it. And then it tries to use it as a gate with this as the input. Okay. So the definition of the add gate specifies that the argument must be a cell of 2 atoms, exactly 2 atoms. So if we give it just a single atom, we're going to get a nest fail error. Okay. Similarly, if we give it a triple of 3 atoms, we also get a nest fail error. All right. So the add gate behavior is specified to require a cell of 2 atoms. There's several other standard arithmetic gates that would do what you expect. So for example, there's subtraction, sub 5-1 gets you 4. There's multiplication, mul 4-3 gets you 12. And there's division, div 8-2 gives you 4. Also power, 2 to the power of 3 gets you 8, right? Okay, so here's an interesting brain teaser for you guys, okay? Let's look at this piece of code, and it's not going to work. If I press enter, it's going to give me a find.add, okay? So what's going on in this piece of code? Why is it doing that? We're setting the cell a equals 1, b equals 2, and then we're using the senhep rune to try and call the add gate on a and b to try and add a and b together, but it's saying find.add. Does anybody have a clue what might be going on here? Yep, very good. So ripweb sidsex says add does not exist in the subject, and that's exactly correct. So recall that everything you type in here is implicitly wrapped in a tisgar with the big dojo subject. However, when we did this, we set the subject manually to literally just the cell a equals 1, b equals 2, okay? And then in that subject, we're looking for something called add, but there's nothing called add defined in here. There's no add in here. So that's why it's failing. It's failing to find a gate called add, okay? However, we can make this code work by just changing one rune, okay? We're just changing that first rune from a tisgar to a tislus. And that works and gives us 3. Can anybody tell me why that now works? Yep, so Sipset Magwen says the tislus rune takes this first argument and adds it to the head of the existing subject. So we're not throwing away the existing subject and wiping it and making it something new. We're just taking this thing and adding it to the front of the existing subject. So that means when we're calling senhep add, we have all the stuff that was already in the dojo subject, including the definition of add. So that's why this works and gets you the result of adding a equals 1 and b equals 2. Okay, so very good. Any questions on that? Okay, so if there's no questions, then we shall be moving on to our next section, which is about Hoon syntax. Okay, so let's talk about syntax. To start off this section, let's consider this very long and complicated Hoon expression, okay? I'm going to type it in the chat for you guys. Let's put it in here, okay? So this image here tells us how to parse this. If I press enter, it gives me the result 32, okay? So what's going on? Well, we're putting 1 and 1 in the cell, and we're adding 1 to 1, which gives us 2. And then we're setting x to be 2, okay? Put 2 and 2, we put 10 and 2 in a cell. We divide 10 and 2, that gives us 5. We set y to be 5. And then finally at the end, we're saying, let's do the power of x to the y, so 2 to the 5th power, and that's going to give us this 32, okay? Um, uh, this is a really long and complicated expression, right? Like it's kind of hard to read this. It takes some mental effort. Um, Fortunately, this isn't the only way that we can write Hoon, okay? The way that we've learned to write expressions so far is called tall form. And although tall form is the most formal way to write Hoon, and pretty much all Hoon has a tall form expansion, we have other more legible ways to write our code, okay? So let's get into some ways that can help us simplify writing an expression such as this. So every Hoon rune has something called wide form, okay? So there's also a wide form in addition to a tall form. So let's see wide form for some runes that we've learned, okay? So Cohort, making a cell of 1, 2. Here's our tall form, right? And the wide form is going to look like this. Cohort, 1 and 2 in parentheses, and only separated by a single space. Okay. Dot less, this is the rune to just add 1 to something. So the tall form was dot less, like that. And the wide form is going to be the single argument in parentheses, like that. Okay. Tisgar, the rune to set something as a subject and do a computation. So recall that the tall form looked like this. Let's set a equals 1, b equals 2 as a subject and get a. The wide form is going to look like this, okay? We're going to put both these arguments in these parentheses and just separate by a single space, okay? Tis less, so it looks pretty similar. Let's use tall form, set 100 to the head of the subject, and then get the head of the subject with this lark notation, this hep. And that's going to give us 100. And we can write it in wide mode like this. Tis less, these parentheses, and 100 and hep. Okay. Similar story for sen hep. I hope we're seeing the pattern now. So sen hep tall form looks like this. And the wide form, we're just going to take those two arguments, put them in the parentheses, only one space in between. Okay. We should go over this tiscol. Okay, so remember this tiscol, we just learned this rune, is to change a bunch of pairs of things at once and then do something with a new subject. So this rune has a tall form, like so. Here, let's set the triple of A equals apple, B equals banana, and C equals cherry as a subject. Then let's use this tiscol to change A to avocado and B equals berry, and then return the whole subject, right? We just did this. The wide form is going to look like this. It's going to look like this. Tiscol, parentheses, A avocado, the first two arguments, then this comma. So the reason comma here is because this rune doesn't know how many pairs you're going to give it. So this comma is telling the parser, hey, like these are the first two pairs, these are the second two, so on, right? Other than that, it looks pretty much like these other wide forms. And this last argument goes here. And does the same thing, okay? We're just changing A to avocado and B to berry. So hopefully you see the pattern with these. In tall form, you're going to use these double spaces or more two or more spaces. You can also press enter in between the arguments. In wide form, you only use a single space, and you surround the arguments with parentheses and you butt it right up against this room. Okay. So any questions on wide form? Okay, so an important thing to note is that we can use wide form as the sub-expression inside of tall form. So you can use wide inside of tall, but you cannot use tall form inside of wide, okay? So for example, let's consider this expression right here. So if we try to type this in the dojo, it actually won't let us. So what are we trying to do? We're trying to use this tis-faz to set x to the value 2, pin that to the head of the subject. And then inside this wide form for the tis-faz, we're trying to use tall form to say, use senhep to call the division gate on the cell 20 and x. So we're trying to set x to 2, then inside there, divide 20 by x, okay? But this isn't going to work because it's improper syntax, because here you're using tall form, and on the outside you're using wide form, okay? However, if we just swap that, so what we're going to do is we're going to change this outside to tall form, tis-faz x2, and then the inside, we can use wide form there, okay? And then this is going to work. This is going to let you compute. Let me prove it to you guys. There we go. So x to 2 divide 20 by x, we get this 10, okay? So point is, always remember, wide goes inside tall, tall does not go inside wide, okay? So now that we've learned what wide form is, let's go all the way back to that long expression, that long 2 to the 5th power expression that we did earlier. Let's try to write it a little more cleanly, a little more legibly, okay? Let's do it like this. Use this wide form knowledge that we just learned. There we go, okay? So this is a little easier, right? Tis-faz x, set x to be the result of adding 1 and 1. Set y to be the result of dividing 10 by 2, and then calculate the power of x to the y, 2 to the 5, all right? 32, boom. Any questions on that? Okay. So let's move on to another type of syntax that we have at our disposal. So some Hoon runes, not all of them, but some of them have an even more readable version called sugar syntax, okay? So not every rune has sugar, but the most commonly used ones tend to have them, okay? So we've actually already used a few forms of sugar syntax. For example, if I make the cell of 1 and 2, that is actually sugar syntax for Cohort 1 and 2. So this cell notation is the sugar syntax for this Cohort, okay? So as I mentioned, runes are organized by family. All the runes that start with Col are used for making cells of things, okay? So let's learn a few more runes in this family and learn a few more sugar syntaxes, okay? Recall that a triple, if you want to make a cell containing 3 things, you do it with this rightwards branching pattern, right? So it's a cell of 1 and the cell of 2 and 3, okay? That's going to be a triple of 1, 2, 3. Now, instead of doing it like that, you can also do it with the rune Colus. So Colus is going to take 3 arguments and directly make that cell. All right. Colus, 1, 2, 3. And this is the wide form, okay? And the sugar syntax for that is literally just making the cell like that, 1, 2, 3. Okay. Similarly, if you want to make a cell with 4 things, we can use this Cohort. Cohort takes 4 arguments and makes the cell with all 4 of them. Okay. The wide form looks like this. And the sugar syntax is literally just typing out the cell like that, okay? And finally, for if you want to make any cell larger than that, there's this Cohort rune. This takes an unlimited number of children. And remember that if the rune doesn't know how many children it'll take, then you have to close it off with this tis, okay? So let's make this Cohort 1, 2, 3, 4, 5, 6, 7, 8. Close it with this tis, and that gives us the cell of 1, 2, 3, 4, 5, 6, 7, 8. And the sugar syntax is literally just that, just what you see in the dojo, okay? So the important thing to note here is that you can have a cell of like 1, 2, 1, 2, 3, 1, 2, 3, 4, 5, and so on and so forth. All these tuples are sugar syntax that do correspond to different runes underneath. However, in cell form, they look pretty similar like this, okay? This is the sugar. So to help us get a little more familiar with sugar syntax, let's consider runes for calling gates. So the Sen family of rune generally has to do with modifying things called cores. We'll learn about that later, okay? But for now, we can just say a lot of the Sen runes have to do with calling gates, okay? Calling gates like add and subtraction, okay? So we just learned this rune called Senhep, and this rune can be used with any gate. And why is that? We can consider any gate to just take a single argument, which is a single noun. However, we can say that noun is a cell containing 1 thing or 2 things or 10 things or 100 things, okay? But we can just consider that as 1 thing, and we can say the gate takes 1 argument. So you can always use this senhep, if you like, for any gate, okay? And it has a sugar syntax, which looks like this, okay? So if I want to subtract 4 from 1, I can write it in tall form like this, senhep sub and the cell of 4 and 1. Or I can write the sugar syntax, which looks like this, okay? So we take these parentheses, and inside it, the first thing is the gate we want to call, and the second thing is the argument to that gate. And then we're going to get the same results, okay? So you'll see this syntax used quite a lot, but you should remember that it desugars to this senhep rune, okay?
Why why are there multiple syntaxes?
So the reason we have multiple syntaxes is to make reading and writing our code easier, okay? So if we go back up to this very long expression, this expression is pretty hard to read, right? But after we learn all our syntaxes, I'll show you at the end, we can turn this into something that's pretty straightforward to read, actually. Okay.
Okay.
So multiple, if you're a computer, if you're a computer reading computer code, you don't need multiple syntaxes. But if you're a person who's reading and writing people code, you want to have your code structured nicely visually on the screen, right? You want to have it a nice flow. You don't want to have lines that are too long. You want to see which parts go under which parts. And all these different syntaxes let us write that to the most aesthetically pleasing and visually communicative way. Okay.
But does it help with like troubleshooting?
Yeah, definitely.
Okay.
Yeah.
Cool.
because you can understand something easier, right? Okay, so back to our sen runes. So if you know that the argument to your gate is a double or a cell of two things, then you can use the rune sen lus, okay? It takes three children. This A is going to be the gate, B is going to be the first argument, and C is going to be the second argument. Arithmetic gates that we just learned. And we can say, we can call it with the sen lus. So sen lus, add 2, 3, 5. Okay, so I didn't have to put these guys inside the cell notation. And the real upshot of this is the sugar syntax right here at the bottom. So that means I can do just like this. Parentheses, add 2, 3. All right. And that's really got to be the easiest and simplest way to call these gates. So you'll see this probably the most inside of Hoon code, but you should know that when you see this, it does desugar to a sen root underneath, okay? All right, so if you know that your gate takes 3 arguments, similarly, there's another rune, sen ket. You haven't learned such a gate yet, but you can imagine that there's this imaginary gate called triple gate. You'd call it like this, sen ket, triple gate, and then A, B, C are its 3 arguments, okay? And the sugar syntax for that rune would then look like this. Yeah. And similarly, if you have a gate that takes some very large number of arguments, there's sen col. It looks like what we've seen. And since we don't know how many arguments it takes here, we have to close it with this tis, okay? And it's just gonna look like this. The sugar syntax will just look like this, okay? A, B, C, D, E, F, so on and so forth, okay? So the point I'm making here is you might call a gate with a 1 argument like this. You might call one with 2 arguments like this, or 3 arguments like this, and 4 arguments like this. And those are all like this is very readable, right? But we should know that when you vary this number of arguments, it corresponds to different runes, different sen runes underneath, okay? And it'll help you when you're reading and understanding Hoon code to be able to switch back and forth between reading something like this and being like, okay, I know that's a sen hep underneath, and then reading something like this, that's a sen lus. Okay, if I need to refactor the code, say I'm giving some really big thing right here, I don't want to write a huge block of code in here, so I'll switch it to the sen lus, so I can put things on multiple different lines. Hassan says sugar diminishes clarity, if I understand correctly. It depends on the situation. Yeah, sometimes it can make things a bit more unclear, but it does usually save space. And yeah, a lot of very experienced Hoon developers will use lots of different sugar syntax, and they'll make their code very compact, very neat, but it also makes it a bit of a puzzle to figure out sometimes. But yeah. Okay. So one more sugar syntax, and we'll move on to the next section. So remember we learned this tis-gal rune, which is just like tis-gar, but with the arguments reversed, right? So here, it's gonna take this first argument and evaluate it with the second argument as a subject, okay? So we're saying, let's evaluate A in the cell of A equals 1, B equals 2, C equals 3 as a subject. And that's just gonna give us 1, okay? The sugar syntax is gonna look like this. It's gonna look like this. So you do this A col, and then this cell of A equals 1, B equals 2, C equals 3. All right. So similarly to wide form, you can put sugar syntax inside of a tall form expression, but don't go trying to put tall form inside of sugar syntax, okay? So with an expression like this, you're trying to multiply 2 in the sugar syntax by the result of adding 1 to 2, okay? So you're trying to multiply by 3. This isn't going to work. I'll even show you, like, see, it's angry. It's making the angry sound. However, we can fix it by just doing like this, okay? Now we've moved the sugar syntax inside of the tall form. Right? Boom. Okay, so in summary, it's good to use sugar syntax in wide form to make your code shorter and more readable, but always remember that you can expand it back into tall form and know how to convert back and forth between them, okay? So to conclude, let's go back to our original very long, complicated piece of code, and let's apply all that we've learned to make it much more readable, okay? So there we go. We're setting x to add 1, 1. We're setting y to divide 10 by 2. And we're doing 2 to the 5th power, okay? So this is quite a bit more readable than this, right? All right. Any final questions on sugar form or wide form? Let me get a drink of water really quick. Okay. So if there's no more questions, let's move on. So last lesson, we began studying things called auras. And if you recall, every value in Hoon is some big number underneath, okay? So 97, okay? And then let's cast it with this syntax that we learned with this ticks. Let's cast this 97 and interpret it as a pat P or an ID for an Urbit chip, okay? And that's going to give us the Galaxy Rook, okay? Alternatively, we can cast the number 97 and interpret it as a pat-t text string. And that's going to give us the letter A, okay? So again, this is just reiterating that there's all these different ways to interpret this underlying data, these underlying numbers. And these types let us do more complicated things than just like looking at numbers, right? So let's introduce a new family of runes for working with auras, okay? This is the Ket family of runes, okay? So let's start with this first rune called Ket Hep. Takes 2 children. The first child is a type specification. So usually you just say, this is a pat P, this is a pat T, whatever, right? The next child is going to be some Hoon expression. And it's going to take that Hoon expression and cast it into this type. If it doesn't fit into this type, you'll get a crash, okay? So let's see an example of this. Let's add 1 to 2 and then use kethep to cast that to a pat UD, which is a number, okay? And boom. It worked correctly. We got the number 3 back. And here's an example of where we'll see a crash. We're going to take the text string hello, and we're going to try to cast it to a pat P ship identity. And we're going to get a type failure. So we need a pat p as specified here, and we have a pat t, this text string, okay? So what does it mean for one aura to fit inside another one? Hoon has a very interesting system here and involves trees. So let's take a look at this diagram here. Basically, if I have some aura pat xy, and then that nests character-wise inside another aura pat xyz, then that means anything of type pat xyz will succeed if you interpret it as a pat xy. So for example, you can interpret a pat ud as a pat u, and you can interpret a pat u as a pat, and you can interpret a pat t as a pat as well. And this means that the empty aura, which is just this pat, this is the master aura, which all other auras can be interpreted as, okay? So one thing to note is you may have noticed that the pat ud aura, which stands for unsigned decimal, it seems to display the exact same data as this pat. So if I take 1, 2, 3 and I cast it to pat ud, I get 1, 2, 3. And if I just cast it to a pat, I also just get 1, 2, 3. So what's going on there? The reason we have these different types is a pat ud is telling you I want this to be a number and I don't want it to be anything else. I want it to be a pat ud, and you can't cast a pat ud to a pat t, okay? So like this. I made this a pat ud and I'm trying to make it fit a pat t and it won't, okay? However, if I take a pat and I try to cast it to a pat t, it'll work. So a pat ud is just saying, I want this to be a number and definitely not anything else. Whereas a pat is saying, this is a number as everything in Hoon is, but it can be mutated into other things, okay? So let's see some more examples of this nesting in action. So pat u fits inside pat ux, right? So pat ux is a hexadecimal number, and I can cast that to a pat u. Pat fits inside any aura, so I can always cast anything to a pat. So if we cast the text hello to a pat, we get this big number. We can cast the number 1, 2, 3 to a pat. We can cast the ship sample palnet, get a big number, and we can cast a floating point, get a big number, okay? Colors are often hexadecimal. Yes, that is correct. However, if we try to take the text hello and use kethep to cast it to a pat ux, we are going to get a nest fail because pat t does not nest character-wise inside this pat ux, okay? So any questions on that? So if we really want to make this hello text and view it as a hexadecimal, we actually can do that though. And we can do it with this syntax that we learned last time. So if we do this tick pat ux tick for this text string hello, we're actually going to get this hexadecimal out of it. So what's going on here? It turns out when we do this tick notation, it's actually a sugar syntax for a double application of kethep. So we're doing tick pat ux tick hello, we're actually taking this hello text string, we're pulling it all the way up the tree and turning it into a pat. We're casting this into a pat, into the raw number underneath. And then we're pushing it down the tree and then making it into a pat ux, okay? So that's why it works. We're taking this, getting the raw data, and then interpreting that raw data as a pat ux, okay? So that's why this works, because it's the same thing. It becomes atomized. One way to say it, sure. All right. So we're taking something that was here, getting the raw data, and then we're pushing it down back here, okay? CabG says, why can't you convert pat ux to pat ud? You can convert pat ux to pat ud. So let's take this. If we try to do it with this kethep, it's not going to work because pat ud doesn't fit inside pat ux, right? This doesn't fit inside of here. However, if we use this notation we just learned, tick pat ud tick, then we're going to get this number, because we're saying take this pat ux, push it up here, and then bring it back down here. Okay. Yeah, good question. Any questions? Yeah, we're taking it to the least precise type, getting the raw data, and then pushing it back down there. Oops. Like that. Yeah. Okay. So in general, how and why will we be using this kethep rune? It's a pretty important rune. We use it as what we call a fence. So we're going to use it to say all the code that comes after this kethep, it has to return something that fits this type. Okay. And you'll see this sprinkled all throughout Urbit code because it's a way to sanity check. Okay, like you're making a chat app and you're returning some message to the front end. Well, you probably should have a kethep to make sure that the message you're sending out is a text type, right? So some of you may have background in programming languages. So here's a little blurb for you, and don't worry if this doesn't make sense yet. Okay, no worries. So Hoon is a statically typed language where all of the validity for the types is checked at compile time when the code is built. All right. So if you put all these ketheps inside your Hoon code, if something's off, then it's going to produce a build error when you're building the code, and it'll tell you, and it'll make you go fix that part of the code. And this is useful because it's not going to let these type errors propagate into code that's actually live and running, right? Okay. Any questions on that? Okay. So coming close to the end of this lesson, one more ket rune we should learn is ketar. So what does ketar do? It takes a single argument, which is a type specification, and it just gives you the default value of the type, okay? So if you have a database and you need to populate it with like empty data, you just use this ketar to get the default value. So what do I mean by that? You do ketar pat ud, you get the number 0. That's the default number. If you do ketar pat p, you get the galaxy Zod. Okay, that's the default planet. And there's also a sugar syntax for this rune, which is just you put this tar right before the type. So like this tar pat ud, the number 0, tar pat p, planet Zod. Okay. All right. So one more ket rune is going to be ket tis. Okay. If you'll recall, Hassan has a question. Is false equal to a number? Yes, false is equal to the number 1. So we can use this dot tis to check the quality. So the sen.n, meaning no or false, is equal to the number 1. Yep, very good. Okay, so ket tis. If you recall, we've previously created structures with faces attached to the parts of them, right? So here we're just going to make a cell where a equals 1 is a head and b equals 2 is a tail, right? It turns out that this is actually sugar for another ket rune, which is ket tis, okay? It takes 2 children, which is, first one is a face or a name that you want to give to something. And that second child is going to be the thing that you want to have a name, okay? So I can just do ket tis a1, and then I get a equals 1, right? We're just saying, let's give the name a to the number 1. And this is the desugared way of writing just a equals 1, okay? So interestingly, it also works on cells by pattern matching. So here we're gonna say ket tis, the cell of the faces A and B, to the cell of the values 1 and 2. And it's gonna make those line up with this A equals 1, B equals 2. And you can do a sugar syntax version like this. So AB equals 1, 2 gets you A equals 1, B equals 2. It's just matching those faces to those values in there. Okay. And with a ket tis rune, you can even do something more complicated like this. We're saying, here's a bunch of faces, here's a bunch of values, okay? A, B, C equals X, Y, and the values 1, 2, and 3, and 4. That's gonna take all these faces and put them on there. And you can do it in the sugar syntax version 2. This equals this, and just attaching all those faces there. All right, so that brings us to the end of our ket runes discussion. Any questions on that? Okay, so one final topic. There's one more feature of the Aura system that we should cover in this class, and it'll get us ready for what we'll learn in next class, okay? So Hoon has a distinguished important type called a term, which is the Aura pat TAS, okay? So based on what we just learned about how auras nest, just knowing this name tells us something, right? Every valid pat TAS must be a valid pat T as well. And in fact, this is true. Pat T is called a chord. It can be any Unicode text, right? Basically any text you see on a computer, pretty much. A pat TAS is more restrictive. So pat TAS can only be the lowercase alphabetical letters, the HEP, the dash, and the 0 through 9 numbers, and the first character must be alphabetical, okay? So let's see an example of what I mean here. So every pat TAS term is going to start with this sen sign. And so we're going to say sen ABC is indeed a proper TAS. Sen cats 1, 2, 3, that's a proper TAS. And sen TERM is a proper TAS. If we do a bunch of random symbols, it's not going to last. That's saying, no, it's not a proper task, okay? So the very special and important thing about this type of text is that every one of these is a type in and of itself, okay? So I can actually use cathep to cast send ABC to a send ABC. And I'll say, yes, send ABC is a send ABC. But I can cast send ABC to a send AB, and it'll give me a failure because send ABC is not the type send AB, okay? So every one of these tags is its own, very own type. And we'll learn very soon why this is important. They're used as tags throughout Urbit's core system and also in app development, okay? So we'll get used to working with these very soon. All right, any questions on terms or anything else that we covered in this lesson? All right, so this brings us to the end of lesson 2. In this lesson, we really started to get a handle on the structure and the syntax of the Hoon language. And in next lesson, we will start to apply what we learn to perform logical decision making, which is an essential part of any computer program. All right, so that's the end of the lesson. Thanks for being here. Let me stop the recording.